Hello, we are at module 9. In this module what we will look at is, we will see how to use the so called Carnot maps or K maps and how to do minimization of Boolean functions. Without using Boolean expressions explicitly, we will see how to derive simplified expressions for Boolean expressions. So, when you do K map based minimization, the purpose of the K map itself is to give you a visual way of doing things. So, whenever we have a 1 in the K map, they correspond to the min terms in the sum of product form, and all the zeros correspond to the max terms in the product of sum forms directly. So, this is something that, so remember, K map is just a rearrangement of the truth table, and wherever you have a 1 in the truth table, you will have a 1 here. Wherever you have a 0 in the truth table, you will have a 0, corresponding thing will have a 0 here. Only that the way in which the table is arranged is going to give us something interesting. And we can combine min terms that are adjacent to each other, which differ exactly in one position. We can combine them, and minimization is done by using these adjacent terms and grouping them. So, we will see a detailed example in a little while. So, there are lots of conditions for grouping. The first thing is, when you have grouping, you are going to do, so we are going to do something called grouping. We are going to group the ones together for sum of products, and we are going to group the zeros together for product of sums. But the grouping has to be done when you have powers of 2. So, you have to pick cells, the number of cells that you have should be a power of 2. Either you can have a group of one cell which is just 1, or you can group 2 cells which are adjacent to each other, or 4 cells which are adjacent to each other, or 8 cells which are adjacent to each other. You cannot do 3 cells and 5 cells and 6 cells and so on. So, it is 1, 2, 4 and 8 and what not. And whenever you group, the next important criteria is, if you are going to group the ones together, they must all have ones if you are trying to get min terms, and they must all have zeros if you are trying to get product of sums. If you are trying to get sum of products, the grouping that you are doing should all be on ones, and if you are going to do product of sums, they should all be on zeros, and they must all be adjacent to each other. So, we will see an example, and I can come back to this slide a little later. Let us see an example. Let us say I am given a function like this. So, I am given a function in which 6 of the 16 rows have ones, and this is a function on w, x, y and z. So, what we have done is, we have laid it out in the form that we have w bar x bar here, w bar x, wx and wx bar. They correspond to 0, 0, 0, 1, 1, 1 and 1, 0. Similarly, these 4 columns correspond to yz being 0, 0, 0, 1, 1, 1 and 1, 0. Now, you go and look at this. Let us argue which of the ones are adjacent and which of the ones are not. So, if I look at the min terms, this is a single term. So, this is just grouping of just one cell. So, this is a grouping of one cell, and what is this cell giving us? It is for w bar, x bar, y bar and z, or 0, 0, 0, 1. Similarly, this cell corresponds to w bar, x bar, y and z, right, or this is M3. This term corresponds to w, x bar, y bar, z bar. So, that is 1, 0, 0, 0 or M8. This one corresponds to M9. This one corresponds to M11. Remember, it is 8, 9, jump to get 10 and come back to get 11. So, this one corresponds to M11. So, you have M8, M9 and M11, and this one corresponds to 1, 1, 0, 0 or M12. So, here we have not really grouped multiple ones together, but we have followed all the properties that we need for K maps. We can only group powers of 2. In this case, each one is a circle and each one is a group by itself. We have grouped 2 power 0 or one term together. So, each one is an individual term. This does not give you any minimization so far. If you took only these and directly wrote the expression, that would be sigma of 1, 3, 8, 9, 11 and 12. There is no minimization. All the min terms would be there. Now, let us look at grouping 2 terms at a time. You look at these 2 things, these 2 ones are adjacent to each other, because visually they are adjacent to each other. So, this is the term corresponding to M1, this is the term corresponding to M3, right. M1 and M3 being adjacent to each other can be combined together. M1 and M3 differ only in the third bit, namely for this y. So, y is 0 in this column and y is 1 in this column, right. So, when you combine them you get M1 M3, and remember I said you can roll the paper out and so on. So, this and this can be combined together. So, M1 and M9 can actually be combined together to give you a term called M1 M9. These two can be combined together to give you a term called M3 M11, because they are also adjacent to each other. And finally, you can combine this and get M9 M11. There are several other combinations of 1s. So, for example, these two 1s can be grouped together, these two 1s can be grouped together and so on. So, all these are listed here, right. So, there are 6 possible combinations with which we can have 2 of them combined at a time. So, now let us take this last step. Can we combine 4 at a time? So, we have these 2 cells which are adjacent to each other, and that combination is adjacent to these 2 cells which are also adjacent to each other. So, you have a combination of 2 which is adjacent to another combination of 2. So, you can combine these 2 and get a combination of 4. So, if you go and look at this and this, that gives you the terms M1, M3, M9 and M11. You can read it from the table also. This is M1, this is M3, this is M9 and M11. These 4 are combined together and that is a term also, right. That is one expression. So, let us look at the simplified expression. So, we have a grouping of 4 here. So, forget this oval and the remark here, we do not need this, the minimized expression does not have it. So, we did several groupings. There are several groupings of 1, several groupings of 2s and several groupings of 4. We start with the largest group. The largest group is a grouping of 4. These 2 are 1s and these 2 are 1s. The largest grouping is a group of 4. I take that and that corresponds to the term M1, M3, M9, M11, right, these 4 terms. Then these ones are already covered. However, these 2 ones are not covered by this group of 4. We take that and the terms corresponding to that are M8 and M12, right, M8 and M12. So, this M1 M3 is this oval, but M1 M3 is a subset of M1 M3 M9 M11. So, M1 M3 need not be covered explicitly. So, we have M8 M12 which covers these 2 ones, M1 M3 M9 M11 which covers these 4 ones. We have all the ones covered. So, which means the expression is done. You can go and write f of Wx yz as sum of these 2 terms, this product M1 M3 M9 M11 and this M8 M12, right. We will see what it means to get this product M1 M3 M9 M11. Let us go and look at these 2 rows again. So, this U kind of thing here and inverted U here, that combines and gives you M1 M3 M9 M11. Let us see what it means. So, in these 4 ones, let us see what is common. So, W bar x bar and W x bar. So, these are 2 different rows in which they are there. However, we see that W bar is here and W is here, x bar is remaining constant, right. Across these 2 rows, x bar is remaining constant, and across these 2 columns, z is remaining constant. So, the intersection of that is M1 M3 M9 M11, where x bar and z is what you need. So, this M1 M3 M9 M11 corresponds to the term x bar and z. So, this is something that you can possibly try out. So, let's do this. I will do this on a piece of paper. Let us look at the term M1 M3 M9 M11, right. So, I want to see how this gets simplified. So, I said that this simplifies to x bar z. Let us see why. So, M1 corresponds to W bar x bar y bar z. So, you can see that 0 0 0 1. M3 corresponds to W bar x bar y and z, because it is 0 0 1 1. 9 is 1 0 0 1. So, that corresponds to the term W x bar y bar and z, and 11 corresponds to 1 0 1 1. So, I can write it as W x bar y and z. So, we have that. Okay. Now, let us see how this can be combined together. So, if I take these two terms, what do you see common here? W bar x bar z is common, then you have y bar plus y. If I take these two terms here, you can notice that w x bar z is common and you have y bar plus y, do not you, right. So, M9 and M11 you have this. We know this is 1 and this is 1, you can write it as w bar x bar z plus w x bar z. Again here x bar is common to both, so x bar z is common to both, we can write it as w bar plus w. This is again 1, this is the same as x bar z. So, you can do all this Boolean minimization and get x bar z. You can also get x bar z by just looking at the terms in the table. So, you look at this table here, in these 4 ones what is something that is common. So, these 4 cells have x bar are in the row which contain x bar and in the column which contains z. However, y is changing from this column to this column and w is changing from this column to this column, those two terms will not appear in the product term. That is what you get from M1, M3, M9, M11. So, think about what you will get from M8 and M12, just for a moment think about what you get from M8 and M12. You can always go and write it as a Boolean expression and minimize it and so on, but if you want to do this visually, I will go and look at the M8 and M12. So, w is there which is not changing, x is changing, so x will not appear in the product term. So, this is w y bar z bar, that corresponds to M8 and M12. So, this term corresponds to x bar z, this term corresponds to M8 M12 which is w y bar z bar. So, this is a very nice and pictorial way of getting these things as opposed to doing all these complicated things that I showed on the paper. We can get to these product terms relatively quickly by knowing how to group. So, let me go back and show you how the grouping is done, what are the rules of grouping, let us see that. The conditions for grouping are min-term groups are restricted to have size that is a power of 2. You can either group just the one term or 2 terms together or 4 terms or 8 terms together and so on. All the cells in a group must have a 1 as their entry if you want to group min terms, or if you want to group max terms they can have zeros. You cannot mix ones and zeros, and all of them must be adjacent to each other. So, these are the 3 different things that we want. Now, to minimize a function, you go and find out the set of groups which include all the required min terms. You should not leave any of the ones uncovered, all the ones should be covered using these ovals or rectangles or whatever you are drawing, right, you should cover them. The function is sum of only those groups if you do the sum of product. If you covered zeros, then you get the max terms and the function is actually the logical and of all those sums. And in general, the larger the group, it is better for you. Go and think about why. We will see this in a little while later, but you for now go and think about why having a larger group is better. So, if I have 4 ones that are adjacent together, instead of keeping the 4 terms separately, it is better to go and group all the 4 ones together. Go and think about why it is so. Now, let us see how the same thing can be done by grouping max terms. So, for max terms, the first thing we do is, you notice that the ones that we had earlier are all in blue and we have put all the other things as 0 which are in a different color, they are in brownish color, right. Now, the rows are maintained as they are 0 0 0 1 1 1 and 1 0, 0 0 0 1 1 1 and 1 0, they correspond to wx and yz, but the interpretation of the rows are now going to be different. So, 0 0 corresponds to the sum term w plus x, 0 1 here corresponds to the sum term w plus x bar, this corresponds to w bar plus x bar and this corresponds to w bar plus x. So, remember this is the logical complement of what we had earlier. So, if you want to interpret it in this product form, you would have written it as w bar x bar, but if you want to interpret it in the sum form, it is w plus x. So, this would have been w bar and x bar, now you interpret it as w plus x. Similarly, this column would have been y and z if you interpret it in the product form, but in the sum form it is y bar plus z bar. So now we are going to do this with product of sums. In the last example I did sum of products. In this example I will show you how to do product of sums. For product of sums we are going to group the zeros together. So we have several things now, let us see how to group them. So let us start with what are all the different max terms. Each 0 is a max term. So this corresponds to the max term m naught, capital M 0, which is the same as w plus x plus y plus z. You can see that by doing a logical OR of this with this. So w plus x or y plus z, that is the term 0 0 0 0. This term corresponds to the row w plus x and the column y bar plus z. So this is w plus x plus y bar plus z. This term corresponds to w plus x bar plus y plus z and so on. So if I look at this term, this is w bar plus x bar plus y plus z. So this corresponds to 1 1 0 0. So you must see that somewhere. So this is w bar plus x bar plus y z. So these are all the different max terms. So 1 1 0 0. Oh sorry, I was looking at a 1, I should look at a 0. Let me pick a 0 here. This corresponds to the term 1 1 and 0 1. So this is 0. So 1 1 0 1 should appear here. 1 1 0 1 is appearing in the list. Okay. So now let us see how to combine them. The same rules as we did earlier apply, except that we are going to group zeros. We are still going to group in powers of 2. We can only group adjacent cells, and for product of sums we can only group zeros. Let us see the various groupings that are there. So this is a grouping because these are 4 ones that are adjacent to each other. So it's a square that we are looking at. Right. There are several other groupings. For example, M4, M5, M6, M7 also forms a group. So this is so let us look at the terms here. M4, M5, M6 and M7, that is this row here. Right. Let us look at this one, M6, M7, M14, M15. So this is M6, this is M6, this is M7, this is M14, this is M15. These 4 zeros are also adjacent to each other. So that is one of the terms and so on. So in this picture I am only showing one of the groupings, I am not showing all the groupings. So this is to get the possible groupings. Now how do you get a simplified expression? We have to cover all the zeros and we want to cover it as few times as possible. This is the thumb rule. We want to cover all the zeros, but we want to cover it with as few groupings as possible and as large groupings as possible at the same time. Right. So fewer but large ones. So let us look at the groupings here. If I started with this one, so I have these 4 zeros taken care of. I still have these 4 zeros and these 4 zeros. So now let us say if I group these 4 together, I will still have these 2 left out. So I cannot expand these 4 into this column because I have a 1 here. Otherwise, if this were a 0, I could have taken all these 2 rows together and combined them into one term. However, I cannot do that now because there is a 1 here. I can only group these 4. Remember, I cannot group 6 of them together, that is not valid. I can only group in powers of 2. So in this case I can group these 4 together and I will still be left out with these 2 zeros here, but they are in this column containing all the zeros. We can group all of them together also and we get various terms. So this grouping, right, is M0246. So this is 0, this is 2, this is 4, this is 6. So we can, this grouping is this sum term and this grouping here corresponds to this sum term and this grouping here corresponds to this sum term. If you notice, all the zeros are covered at least once and we have tried to cover it with as large a 0 group as possible, which is still a size of powers of 2. So these are the 3 different sum terms that we get: M0, M2, M4, M6, M5, M7, M13, M15 and M2, M6, M10, M14. These are the sum terms that we get. Now we can go and write the expressions for this directly by looking at M0, M2, M4, M6. So let me show you how to get the corresponding expression for M0, M2, M4, M6. M0, M2, M4, M6. So the product term that, so remember this is a set, it is not a product of these 4. So the sum term that corresponds to this should have this one, right. So in some sense you go and look at this one. So this is W plus X plus Y plus Z. M2 is W plus X plus Y bar plus Z. M4 will correspond to W plus X bar plus Y plus Z, and M6 will correspond to W plus X bar plus Y bar plus Z. If you look at these 4 terms, right, you can notice that what we are having is this W is appearing in the same form in all the 4. So you can notice that here W is appearing in the same form everywhere, and Z is appearing in the same form everywhere. So the combination of these 4 is actually just W plus Z. Right. You can infer that by coming back and looking at the table here. So these 2 rows have W in common. So the sum term should have W. If you look at these 2 columns here, which this has Z in common, this is Y plus Z and Y bar plus Z. So these 4 cells have W plus Z, and similarly these 4 cells we have X bar in common, and in these 2 columns we have Z bar in common. So these 4 cells correspond to X bar plus Z bar. Finally the last column here, W and X are continuously changing, but this corresponds to the term Y bar plus Z. So this one is W plus Z, this one is X bar plus Z bar, and this last column is Y bar plus Z. You can write that as a simplified Boolean expression, W plus Z into X bar plus Z bar into Y bar plus Z. So in this example we have grouped the zeros together and we got a product of sums. So let us look at some more examples from here. So if I have a table like this, right, this is a expression where we have, it is a function of X, Y and Z. Let us assume that X is the leftmost variable and Y, Z appear in the next 2 columns in the truth table. If I want to group them together, right, the sum of products will be grouping all the ones together. So we have a group of 4, and in this group of 4 it corresponds to Z being 0 as a column, so it is Z bar, and this one is still left out, I have to group that also. When I do that I get the term X bar Y, because it is in the row X complement, but it is across 2 columns where Z is flipping but Y is constant at Y, right, it is X bar Y. So it is Z bar plus X bar Y. If you want the same thing in product of sums, you group the zeros together. So if I group these 2 zeros together, that will correspond to the term Y plus Z bar, and if I combine these 2 together, it corresponds to the term X bar plus Z bar, sorry, Z bar, because Z is 1 here. So this row corresponds to X bar, these 2 columns correspond to Z bar, so it is X bar plus Z bar. You can actually go and take this expression and simplify it, you will end up with the expression on the left side. So you have product of sums and sums of products, right. In this example, if you want to implement this using gates, the Z bar plus X bar Y will require 2 inverters, because for Z and X you need inverters. There is one AND gate here and one OR gate here. So we have 2 inverters, one AND and one OR gate. So this 2 here implies it is a 2 input gate. If we do the product of sums, we need 2 inverters, one for Z bar and one for X bar. We need one AND gate to do this product, but we need 2 input OR gates, one for this term and one for this term. So in this example, right, it looks like this one needs 4 gates and this one needs 5 gates. So for example 1, the sum of product expression, this way of simplifying is better rather than this way of simplifying it. Let us look at one more example. So this is an example in which we have 4 variables W, X, Y and Z. let us group the ones together and get sum of products first. So let me show you the one which is not grouped. We can see that there is a group of 4 ones here, 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 and so on. There are several groups of 4 here. So let us pick all the things that we need. So there are 4 groups of 4 here. So this term corresponds to W being 1 and Y being complemented. So you have W Y bar. This column here corresponds to Y being 0 and Z being 1. So you have Y bar Z. This row here corresponds to W being 1 and X being 1. So you have W X. And finally this group of 4 corresponds to X being 1 and Z being 1. So you have X Z. So f of W X Y Z is W X plus W Y bar plus Y bar Z plus X Z. So this is a very simplified expression for this truth table that is given here, or the K map that is given here. So if you do the product of sums, the product of sums will require you to group the zeros. So there is a group of 0 here and a group of 0 here, that is 2 groups of size 2, so it makes it a group of 4, and there are 2 groups of size 2 here which can be combined to make a size of 4. So you look at this term here and this term here, right, that corresponds to the fact that W is 1, and these 2 columns correspond to the fact that Z is 1. So the intersection of that gives you W plus Z. And if you look at this grouping here, this corresponds to the fact that X is 1 and these 2 columns, so these 2 rows correspond to, so the first row and the last row correspond to the fact that X is 1, and the last 2 columns correspond to the fact that Y is 0, the intersection of that gives me X plus Y bar. So this is the sum of product and this is the product of sum. In this case you will need 1, 2, 3, 4 AND gates, 1, 2, 3 OR gates and 1 inverter, right. Only for Y you need an inverter. So 1 inverter, 4 AND gates and 3 OR gates, whereas in this one you need 1 OR gate here and 1 OR gate here, 1 AND gate here and 1 inverter there. So 1 inverter for Y bar, 1 AND gate for the product and 1 AND gate for the product and 2 OR gates for the individual terms. So in this example it so turns out that the POS is smaller. Upfront you may not be able to say whether SOP is better or POS is better. In this example POS is better, in the previous example SOP form was better. So let us wrap this module with some equivalences. We already did this. So inverter is equivalent to ANDing the inputs of the, so connecting the same input to both the inputs of a NAND gate, and AND followed by an invert, so NAND followed by an inverter is AND. If you invert the inputs and give it to a NAND gate, that is equivalent to an OR gate, and if you attach an inverter to the output of this circuit here, that gives me a NOR gate. So this is just for you to recollect what we did so far. So let us see, if we want to implement a function like this using only 2 input NAND gates, right. So xy plus x bar yz, we want to implement this using only 2 input NAND gates, then we can do something like this. So this is xy, we AND it together, you have it here, then this is x bar yz, ANDed it together and you logically OR it. So this is an AND OR circuit, right. So you have the inversion for the literals and then you have a AND set of AND gates which give you the product terms, and then you put an OR gate that gives you the sum. So you are given a sum of product and you have the circuit implemented using AND and OR. But the question is asking you to implement this using NAND only, and not just any NAND, it is asking you to implement using only 2 input NAND gates. Let us see how to do something like this. So the first thing we are going to do is substitute all the logic gates by equivalent 2 input NAND gates. So we will see, so if I take this circuit, I substitute that with 2 input NAND gates, that is what the circuit that you have in the bottom is what we will get. Let us see how. So this inverter is here, this AND gate is NAND followed by an inverter. So, that is there, and this 3 input AND gate is actually written as a combination of two 2 input AND gates. So, this circuit is actually written up as a combination of two 2 input AND gates. You can see that there is a NAND followed by an inverter, and there is another NAND followed by another inverter. So, it is essentially a cascade of 2 AND gates. So, if I want a 3 input AND gate, you can do something like this. So, let us see how to get a 3 input AND gate. So, if I want a 3 input AND gate, this is equivalent to writing it as one 2 input AND gate followed by another 2 input AND gate, right. And to get this AND gate, we have a NAND followed by an inverter. To get this AND gate, we have a NAND followed by an inverter. That is what you see in the picture here, right. So, coming back to the slides, you can see that this NAND followed by the inverter is one of the 2 input AND gates, and this NAND followed by this inverter is taking care of the other input. So, it is a cascade of two 2 input AND gates, and finally, this is how this is an OR gate. You can see the structure here. There are 2 inputs which are complemented and is going to an AND gate. So, that means it is an OR gate. So, what we have now is we have taken an AND OR circuit and redrawn that using only NAND gates. So, in this picture you can notice that there are NAND gates and nothing else. So, the only extra thing seems to be this for Z, instead of taking Z and putting it directly here, here we have it as Z and 1 complement, which is Z bar, and complement of that, which is Z. So, we have Z, instead of giving a line directly to this NAND gate here, we have it as a NAND with 1 followed by an inverter, that is the same as Z itself. So, this has only 2 input NAND gates and nothing else. Now, this is not the most simplified form. One thing we can do is remove redundant NAND gates. So, when is something redundant? So, let us see when something might be redundant. If I have a circuit in which I have an inverter followed by another inverter, let us say I give you this as X and this as F. An inverter followed by an inverter is actually redundant. Two inverters actually cancel their actions. So, this is equivalent to saying X is F itself, is it not? So, the same thing that we can do in the NAND gates also. Whenever we see an inverter followed by another inverter, we can remove those two inverters and connect them with a wire. So, in this picture if you notice, this inverter, right, this is an inverter and this is an inverter, but implemented using a NAND gate. So, this is a function which is doing inversion, this is also another gate which is doing inversion. So, I take inversion and inversion here, inversion of inversion is just the wire itself. I can remove that wire, and there are other places where you can do the same thing. So, this is an inversion, this is an inversion, I can remove the two inversions together and get rid of it. Similarly, this is an inversion and this is an inversion, I can get rid of that also. So, this wire corresponds to these two inversions being ridden off. Then this wire is the same as these two inverters and getting rid of one, and finally these two inverters, when you get rid of it, we have a wire. So, in this circuit we have 1 plus 6 7 gates plus 2 9 plus 3 12. So, this direct implementation has 12 2 input NAND gates, whereas once you get rid of the inverters, we got rid of 3 inverters. So, this gives us a circuit with 9 2 input and NAND gates. So, this is better than the circuit that you have here. So, if you notice this circuit is actually doing the same thing as the AND OR circuit that we did before. It is actually doing the same thing as this circuit here with the redundant gates, only that it is simplified. It has much fewer gates than this one here, and it satisfies the problem statement that we started with, implement using only 2 input NAND gates. Right. This brings me to module 9 of this week, and what we saw in this module is we saw two parts. One part in which we did some minimizations using the truth tables, and the second part of the module in which we saw the writing circuits in terms of a specified structure of the gate. So specifically we looked at using only NAND gates I will give this to you as an exercise. Take this circuit that is given here, this circuit, and implement that using only 2 input NOR gates, and figure out the number of gates that you need for it. What is the smallest number of gates that you need for implementing this circuit using only 2 input NOR? Go and think about that. So this brings me to the end of this module. So we have a few more modules to look at for this week. So I will see you in a little while. Thank you.